Good morning, good afternoon or good evening, depends on where you are and what time of the day it is. My name is Mr. Kanwar. I am a science director and I'm delivering home learning video lesson 1, which is for year 8 students. So if you are a current year 8 student, this is for yourself. So you've previously done some energy work and this is a carry on. So this is your first video lesson, and this is because you've either missed lessons 1 to 3. So this is week 1 in the school. You've either missed lesson 1, energy transfers and calculations, lesson 2, the difference between temperature and heat, and lesson 3, heat transfers. So if you missed any of those lessons, or you are catching up on work in regards to any of those 3 lessons, then this is the video for you. If you are missing different lessons, then you may want to go on a different video. So once again, this is for year 8. The topic is energy, and it is on energy transfers and calculations, temperature versus heat, and heat transfers. So as with everything, we go through our learning journey, and just to explain that, within energy, we start off with energy transfer calculations. Now you would have done, or you should have done, some work in year 7 in regards to some basic energy when we talked about energy stores and energy transfers. This topic moves further on and we're talking about energy transfer calculations. So within this video, what I will be going through is not only energy transfer calculations, but measuring heat and temperature and heat transfers. So I'll be going through all 3 lessons. So we'll have quite a few aspiring challenges, but what we are planning to do for this part of the lesson is recall the law that energy can neither be created or destroyed. It can simply be transferred. Now that, if you remember that, that is it. That's all you need to remember. And then our aspire, apply this knowledge to a variety of energy transfer calculations. So that's the first part of this lesson. So when we talk about energy and we talk about whether it's made, I think it's a common misconception. People think that energy can be made, and in actual fact some people will say energy can be created, or I have made energy. No, you haven't. You can't. Energy cannot be created. It can also not be destroyed. What happens is it moves into a different form of energy, or it transfers itself to a different energy store. It cannot be created. So a common mistake is that people think in biology lessons in particular, mitochondria, so within the cell, it produces energy. Wrong. It does not produce energy. It releases energy. That's totally different. It releases energy, because that means it must come from something else before. You can't simply produce it. So the word create, produce, make, when it comes to energy, will not work. So energy cannot be created or destroyed. It is simply transferred from one type of energy to another. And that is called the law of conservation of energy. What you will need to be able to do is you will need to be able to recall that simple definition. So if it helps you, write it down. Pause the video, write that down, and that will simply get your challenge done. What I'm going to get you to do now is we're going to have a recap of particularly all the year 7 work that should have gone previously. So I'm going to give you 10 examples. What I want you to do is write down the main energy changes that are happening. I'll give you around about 15 seconds. I will read the question to you, and then straight after I will give you the answer. So what I'm going to ask you to do is to write down the main energy changes. For that to happen, you need to think back to all those energy stores and transfers that you can remember. So think about kinetic energy, heat, thermal energy, potential energy. Now you can get different variations of that, kinetic energy and so forth, but you will need to make sure that you have got all of those down. Right, hopefully are we ready? So number 1, we've got some loudspeakers. It changes something energy transferred in the wire into something else energy transferred to the air. So I'll give you 20 seconds. So loudspeakers change something energy, which is transferred in the wires, into something else energy, which is transferred to the air. Let's have a look at our answer. So loudspeakers, I'm sure hopefully most of you got it. If you didn't get it, then I think you'll understand where we're going with this activity. It changes electrical energy, because the electrical energy is transferred in the wires, into sound energy, because obviously that's the point of the loudspeaker, that you can hear. So the electrical energy comes from the wires, it changes into sound energy, and that's transferred through the air. So electrical and sound are your answers. Number 2, a man falling down is changing something energy store into something else energy store. So a clue, a man is falling down is changing. So assume that at some point he would have been stood at a point and energy is being transferred from something store, think about the height, think about why is he falling, energy store, into something else, and whilst he's falling he's clearly moving. There is your clue, into that energy store. Let's have a look at that answer. So what we've got is gravitational potential, because he is falling from a height, and initially he would have had potential energy store, so anything from a height would have potential energy. Once you say let go of it, it changes into the kinetic energy store, which transfers itself into the kinetic energy store, I should say. So gravitational potential energy store into the kinetic energy store. That's what's happening with that guy. Number 3, we've got a simple electrical circuit with a light bulb that changes. So what's stored in the battery, it then turns into some other energy which is transferred in the wires. We've already had this one, a clue. And then into some other energy stored in the bulb, and then some other energy transferred to the room. That last one, think about what else that light bulb is perhaps, and I think the animation actually helps, what else the light bulb may be emanating, and that is a clue. If you don't know what the word emanating means, then you need to look that up, but even so, the clue is with the little dashes around the light bulb. I'll give you 10 seconds. Right, so let us see. We've got, in a simple electrical circuit with a light bulb, changes chemical energy, that's obviously stored in the battery, the chemical, into electrical energy, and that's transferred in the wires. And then it goes into thermal energy, which is stored in the bulb, and light energy, which is transferred to the room. Now I'm looking at that, and you can see that you've got thermal energy and light energy coming from the electrical energy. Okay, let's go with. So number 4, a hairdryer changes something energy, which is transferred in the wires. Again, we should be pretty good at that one, into some other energy stored in the moving air. Something else and something else both transferred into the room. I think the image gives you an idea. Think about what a hairdryer does. I'll give you around 15 seconds. So think about what a hairdryer does. I think the guy's over exaggerating slightly. I'm not sure my eyes would pop out using a hairdryer, but even so, he needs to clearly get a new hairdryer. So let's have a look. So a hairdryer changes electrical energy, which is transferred in the wires, into kinetic energy, which is stored in the moving air, and thermal energy and sound energy both transferred into the room. So we could argue that sound energy is rather wasted. It's wasted energy. Thermal energy is what we actually want it to, because that produces the warmth required to dry the hair. And obviously kinetic energy because the particles are moving, and it's from the electrical energy. So there we go. Number 5. When an arrow is released, the bowstring in a bow will change something energy stored in the stretched bow into some other energy stored into the moving arrow. Now we've done moving, so anything that's moving is a certain type of energy, with some other energy transferred to the surroundings. So think about the bow, plus another type of energy. I'll give you 10 seconds, I'll give you 15 seconds to think about it. So let's have a look at the answer. When an arrow is released, the bowstring in a bow will change elastic energy, as you can see, stored in the stretched bow, into kinetic energy, stored in the moving. So remember when I said moving and kinetic? That's because the arrow is moving, with some sound energy transferred into the surrounding. So you'd get the sound energy that is transferred into the surroundings. So that's what will happen with that one. Number 6. We've got a burning candle is changing something energy stored in the candle into some other energy transferred to the room, and some other energy transferred into the room, and even some other energy stored in the moving air above the flame. Now let's repeat that. That's quite a tricky one. So what you need to think about is when you've got a candle and it's burning, what does the flame actually do? I'll give you around about 10 seconds. Right, let's have a look. A burning candle, I should say, is changing chemical energy stored in the candle into heat energy transferred to the room, a light energy which is also transferred into the room, and even some kinetic energy stored in the moving air above the flame. Now that one was particularly difficult. Yeah, so good job if you managed to get that, because what's surprising about that is that the air particles above the flame are moving. You can feel it actually, because obviously you can feel the heat energy when it's getting transferred. So if you got that you've done very well. So give yourself a pat on the back. Chemical energy is stored in the candle. That's from the wax, and it changes into heat energy and obviously light energy, which is why you see it. So number 7. Fireworks change some sort of energy, which is stored in the firework, into some other energy, another energy, and a final energy, all transferred to the surroundings. So think of a job of a firework. That should give you a clue. I'll give you 15 seconds. Right then, let's have a look. So fireworks change chemical energy, which is stored in the firework, into thermal energy, because it does produce You can feel it produces heat. Sound energy, because obviously what's the point of having a firework if it doesn't go bang? And light energy, and also what's the point of having a firework if you can't actually see it? All transferred to the surroundings. So that's what happens with the fireworks. Change chemical energy into thermal, sound, and light energy. So that's number 7. Number 8, a green photosynthesizing plant is changing some type of energy transferred to the plant from the sun into some other energy stored in the plant. Give you 15 seconds to think about that one. Right, let's have a look. So the answer to number 8, we've got a green photosynthesizing plant is changing light energy, which is transferred to the plant from the sun, into chemical energy stored in the plant. So that is what we've got occurring there. Right, I do think that we've probably done, although I did say we were going to do 1 to 10, I think we have done 1 to 8 is more than enough on this. I think you've got the hint in terms of the energy transfers. What we now need to move on is to use the calculation and to understand that energy could be either wasted or it could be useful. So let us move on to that. So how can we show that? This is a diagram, it's called a Psyche diagram. Now, what I could ask you to do is explain what this diagram tells us about the energy transfers in the bulb. What I'm going to do is I'm going to give you 30 seconds to think about what do you think it is showing us actually, before I give you an explanation as to what. Look at the diagram very carefully. There's a reason why it's drawn on kind of graph paper or squares. I'll give you 30 seconds. Right then, let's have a look. So what we've got, I'll get my trusty pen. What we've got is we've got 100 joules of electrical energy. Now, what we can do, and I'm sure you noticed this is 100, and we've got 1, 2, 3, 4, 5, 6. Hopefully you can follow where I'm writing in green. 7, 8, 9, 10. So we've got 10 boxes there. Now, this is like a histogram. This is actually to scale. So we've got 100 joules and then we've got 10 boxes. So basically each box is worth, so 1 square, yeah, I have to figure my writing. Ooh, 1 square is equal to 10 joules. Okay, that's what that tells us. And then 40 of those joules, and I use a different colour, 40 of those joules turns into light energy. So that's an energy transfer, and that is useful because obviously that's what a light bulb does. So therefore it's useful. Whilst 60 turns into heat energy, and that's wasted because that's not what we want the bulb for. Mind you, a bulb turning warm isn't a bad thing necessarily because it obviously would keep you warm. Even so, that is not the point of a bulb. So what we've got is we've got 40 that is useful, 60 that is wasted. So we could come up with like a percentage. We could say that the efficiency of this bulb is 40, which is useful, divide by the total, times by 100 because we're doing a percentage. And it's really easy. We get 40%. So the efficiency of that bulb is 40% because it's 40% useful. The rest of it is just wasted. Okay, so that's a Psyche diagram. Really, hopefully straightforward. But that's the start of when we start talking about energy transfer calculations. Let's have a look at another one. So again, we start with 100 joules of kinetic energy. And again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 boxes, one box, one square I should say. One box, although I'm calling it a box again, one box square, one square is equal to 10 joules. Okay, so useful, we've got 30. Well, what we're doing, or the question is, let us complete the missing two energy values for the diagram of the wind turbine energy transfers. How does this, poor grammar, how does this show the conservation of energy? So we've got 30 joules, that's useful. We've got 20 joules, that's heat. How are we going to work out the kinetic and the sound? I will give you 30 seconds. Okay, let's have a look. So what we should have got is 40 joules for kinetic energy and 10 for sound energy. And how do we know that? Well, if we look very carefully, this comes from there. So if we go back, we can see where it comes from. And we've got 1, 2, 3, 4. And even if we didn't go back there, we can go across here. 1, 2, 3, 4. And we know that each box, as I've called it, or what each square is worth 10 joules. So that one would be 40 joules. And then when we go to this one, I'm running out of colours, aren't I? I've put so much squiggly lines everywhere. This is one box. There. So one box. So that's 10 joules. So that's it. That's as easy as that to work out. Now what's actually useful? Well, if we wanted to work out the efficiency of this, we know that 30 joules is useful. Yeah. So again, we do useful, which is 30, over total, which is 100, times by 100 because it is a percentage, and that is equal to 30%. So that wind turbine is 30% efficient. Okay, so that's when we're calculating efficiency. However, we can also calculate something called gravitational potential energy. Now, this goes back to the diagram of the falling guy. So you've got someone who is falling. Well, you've got someone at some point who was falling. Or you've got something at a height. At GCSE, you will need to remember the equation that allows you to calculate the amount of GPE, I'm now going to call it gravitational potential energy, that an object has stored in it. So for example, if you were to pick up your pencil, just pick it up. The moment you pick it up, it has gained height. Now we know when we let go it's going to drop. However, is it going to have, is it going to have more energy stored in it if you picked it up and put it way above your head, or if you just picked it up and just put it slightly above the table? Now the obvious answer, and I know what you're thinking, is yes sir, I already know that. If I put it above my head, it's going to have more energy because it's going to fall and it's going to hit like that the table. However, a pencil not far from the table is not going to make that sound. And the reason is because it's got more energy. We know that. But what's that in relation to? It's in relation to the height. So GPE, gravitational potential energy, is really to do with the height of the object. The gravitational field strength doesn't change on Earth really. Now, technically, as you go up through the atmosphere, it does slightly alter. However, for the most part, we learn it as the number 10. So it's just 10 newtons per kilogram. That's the gravitational field strength. Now, if you're on, that's on Earth. If you're on Mars, it would be lower. If you're on Jupiter, it would be higher because the gravitational field strength would be weaker on Mars, stronger on Jupiter. The mass is measured in kilograms. So that is the particle matter. So the mass is measured in kilograms. That's not going to really change, but what will change is the height. Obviously, when you've got a pencil, it's not going to change mass as you move up and down, but it will change height. It won't really change gravitational field strength. So going through that equation, mass is measured in kilograms. Gravitational field strength is measured in newtons per kilogram, usually 10. Height is measured in meters. Remember, there's 100 centimeters in 1 meter. And GPE is measured in joules. That's the unit for energy. And obviously 1,000, I say obviously, but 1,000 joules is equal to a kilojoule. So that's the equation. Let us work some examples out. So you lifted a set of books of mass 3 kilograms for 2 meters. Okay, what is the gravitational potential energy gained by the books? Take G equals 10 meters per second squared. So the first thing we should always do, and I'll do this for you, is GPE, you can see my great writing, equals mgh. So that's mass times gravity times height. Gravitational field strength, I should say. I'm going to give you 15 seconds to work it out. So we've written the equation. Now what we need to do is substitute. Right, so what we should have got is this. So GP equals mgh. We've got 3 because 3 is the mass. Where did we get that one from? There. 10 is the gravitational field strength because the question tells you. And 2 is the height because that is what it has been lifted. Times those numbers together and you get 60 joules. Fairly straightforward, hopefully. Hopefully you got that right. Let's try this one. No clues. So you've got a mass of rock, 75 kilograms, 4 meters above the height. Calculate the GPE stored in the rock. Assume you are on Earth, so the gravitational field strength will be 10. Bizarrely, what you might be able to hear is a helicopter in the background. Right, let us see what you've come up with. So again, we write the equation down. Mass times gravity times height. The mass is 75. Where did we get that one from? Because it tells us in the question. Height, where did we get that one from? There, because it tells us in the question. Now, because we're on Earth, we have to assume that the gravity is 10. Times those numbers, we get 3,000 joules. Now, sometimes what we could do is we could convert that into kilojoules. So it's 3,000 kilojoules. So there we go, 3 kilojoules or 3,000 joules, because there are 1,000 joules in a kilojoule. There we go. So we've used the gravitational potential energy calculation. Now we can move on to part 2 of this lesson, where we're measuring heat and temperature. This is going to be quite a short part, because essentially what we need to know is the difference between the two. So that's what we're going to do. So describe what heat and temperature are is our challenge, and then explain the difference between heat and temperature using examples. Well, what we can do straight away is we can just pretty much go into what the definitions are. Now start from the bottom. So we've got temperature. So the temperature of an object is to do with how hot or cold it is. It's measured in degrees centigrade, and it's just make sure that you write this properly. It's with a little o, which is lifted up. It's also known as superscript. So you lift it up, and then the C. I'll just point it out if you can't see that. It's not those two though. Okay, so you just have to be quite clear with that. So the temperature of an object is to do with how hot or cold it is. So what's heat then? So heat, the heat an object contains is the amount of its thermal energy measured in joules. So temperature tells us how hot or cold something is. Heat doesn't. That tells us the amount of thermal energy there is within an object. So if there's lots of thermal energy within an object, you can pretty much guarantee that the temperature will be high. If there's very little thermal energy within an object, then you can pretty much assume that the temperature will be lower. That's the principle. What you will need to do is pause the video and get those two definitions down, but have that understanding of what I've just said. So heat, the heat an object contains is the amount of its thermal energy. Let me just think about that again. So it's the amount of its thermal energy. So thermal energy, if there's a large amount of thermal energy, then it will be hot. If there's a small amount of thermal energy, then it will be cooler. I'm not saying it's going to be cold, but it will be cooler. Okay, so there's your heat and temperature. Let's look at some examples. So example 1. A swimming pool at 30 degrees Celsius is at a lower temperature than a cup of tea at 80 degrees Celsius. So a swimming pool at 30 degrees Celsius is at a lower temperature than a cup of tea at 80 degrees Celsius. But the swimming pool contains more water, so it stores more thermal energy than the cup of tea. So why isn't it at a higher temperature? Let's have 10 seconds to think about it, and I'll explain it again. So think about this. A swimming pool at 30 degrees is at a lower temperature than a cup of tea at 80 degrees. Now that makes sense. Well, why wouldn't it? But the swimming pool contains more water, so it stores more thermal energy. So it's got more thermal energy than the cup of tea. So if it's got more thermal energy, why is it not at a higher temperature? Let's have a look. It's all to do with the number of molecules in the pool. So there are more molecules in the pool, obviously, because it's larger, so you can have more molecules. And the temperature of the pool refers to the average heat energy per molecule. So you've got more molecules and it's spread out more. As there are so many molecules, the temperature is lower than that of a cup of tea with fewer molecules. Because obviously within a cup of tea, you're nowhere near going to have as many molecules as a swimming pool. So therefore, the thermal energy, the average heat energy per molecule, will be lower. Now, hopefully that makes sense. So you've got more molecules in the pool, therefore it's spread out more. Therefore the temperature is going to be lower, even though the thermal energy in total is probably higher in the pool. Well, it's definitely higher in the pool than it is in the teacup. Example 2. To boil water, we must increase its temperature to 100 degrees Celsius. It takes longer to boil a large beaker of water than a small beaker of water because the large beaker of water contains more water and needs more thermal energy to reach 100 degrees Celsius. Why? So to boil water, we must increase its temperature to 100 degrees Celsius. It takes longer to boil a large beaker of water than a small beaker because the large beaker contains more water and needs more thermal energy to reach 100 degrees Celsius. Now, so if we're going to boil the water, we have to increase its temperature to 100 degrees. So it takes longer to boil a large beaker of water than a small. That's because there are more molecules. Simple as that. Because there are more molecules, it takes longer for it to reach the average temperature of 100 degrees Celsius. Therefore, it needs more energy in the first place. Okay, so there's two examples of the difference between heat and temperature. So again, I'm going to give you 10 seconds. What is heat? Say it. Should have said the heat of an object contains, well, the heat an object contains, I should try and get my words out properly. The heat an object contains is the amount of its thermal energy measured in joules or J. However, temperature of an object is to do with how hot or cold it is measured in degrees Celsius. Okay, so there are your two, heat and temperature. If you need to write it down, so you just make sure that you know what the difference between the two is, I shall read this out to you, and you're very welcome to copy this down in your book or your notes. So, the hotter an object is, the faster the motion of the molecules inside it. Yep, because they've got more kinetic energy. Thus, the heat of an object is the total kinetic and potential energy of all the molecular motion inside that object. Ooh, technical that. It's not difficult though. Thus sounds posh. Anyway, the heat of an object is the total kinetic, so the moving ones, and the potential energy, therefore the non-moving ones, of all the molecular motion inside that object. Temperature, on the other hand, is a measure of the average heat or thermal energy of the molecules in the substance. Heat is measured in joules using a calorimeter, and temperature is measured in Celsius using a thermometer. Okay, so there we have our heat and temperature. Third part of this lesson is moving on to heat transfers. Okay, so we're moving on to heat transfers now. So what we're going to do is describe the three methods of heat transfer. You may actually know this, and then apply knowledge of heat transfers to explain the most effective method of making popcorn. Now what I'm going to do is I'm going to allow you to think about that aspire. I'm not going to go through that within this lesson because you need to be able to explain the most effective method of making popcorn. So think about how would you make popcorn the most effective way, but it would use one of these three methods of heat transfer. So let's get crack straight into it. We have got conduction, convection, and radiation. So if you need to write those three down, they are your three methods of heat transfer. Right, we're going to do conduction first. Now that occurs in solids. It's relatively straightforward. It is when hot particles vibrate a lot. So what you've got is you've got some hot particles. They are vibrating and energy is transferred. Let me get my arrows here. Energy is transferred as so through vibrations. So it moves along like so. So it starts here. You heat this up. Let's say you've got a Bunsen burner here. That's my Bunsen burner sound. It's heating those particles. It then vibrates, passes on the heat, and eventually it'll all get hot. Cool particles don't vibrate that much. So conduction occurs within solids. Convection only occurs in fluids. Now, some of you might think, liquids. Well, fluid is a liquid or a gas. So you might have known that, you might not have known that, even so, it's a liquid or a gas. So, one part of the fluid gets heated. The particles move around with more energy. Okay? So hot particles end up being more spaced out. So they are less dense and rise. So what we've got here, you can see on my little animation, we've got heat. These particles gain more energy. They gain kinetic energy. They start moving about. Because they get further away from each other, they become less dense and they start to rise. When they're up here, they lose their energy or gets transferred somewhere else. Therefore, the particles start to condense. They get closer together, they become more dense, and it starts to fall. And this cycle continues as so. I'm going to run out of space in a second, but it keeps going like this. And it'll keep going round and round as long as there is heat energy being added into it, into that cycle. So what you've got, let's be clear about this, particles gain energy, they get further apart, less dense, rise. They lose energy, close together, more dense, and fall. That's convection. So the third one is radiation. This one is special, doesn't require particles, so it's quite an odd one. So conduction, convection require particles. This one does not require particles. So heat moves from one place to another using something called radiation. This heat radiation is infrared energy waves, and that occurs at the sun being a prime example of that. So particles move from one side to another. They can move within a vacuum. So a vacuum is a space where you have no particles. Think about your windows at home. Your windows may be double glazed. There's two panes of glass. In between there should be a vacuum. And the reason why there's a vacuum is then conduction and convection can't occur. So therefore it makes it more efficient. The only thing that can happen is radiation. So when you sit next to a window and the sun's there, the sun's on the outside, you can feel the rays coming in because that's the radiation. And so radiation can move through anything. Well, move through air at least. So, in summary, we have types of heat transfer. Conduction, that only occurs in a solid. Convection only happens in fluids, liquids and gases. And radiation does not use particles. It is pure heat energy and can occur anywhere, even in a vacuum. Okay, so they are our three energy types. I'll leave it up for 20 seconds whilst you copy that down because you definitely do require that. Okay, hopefully you got that. So what I'm going to show you is some radiation. So this demonstration is called Light the Match. It's done by the University of Michigan, and let's see what happens. Okay.
So this is a video explaining how to get this experiment set up, the Light the Match experiment, to get everything lined up in order to be able to light the match. So the first step is to grab our 1200 watt light bulb, attach it to a variac so we can control the amount of output for this lamp. The next step is then to focus the point on the opposite mirror in order to get all of the power focused at the right focal length. So what I do to start is turn up the power just enough so that I can see the reflection of the light on the other mirror. The next step is to then get the height of the light correct so that it is in the center of the mirror. So in order to do that, I move this up and down until I find that position. Once I'm semi-confident with that, I then get the focal point of the lens correct so that it's focused on that piece of paper where we will be putting the light or the match. So move it up and down, left and right, until we get the focal point right where we're going to be placing that match. So, Once we have that set, we remove the image plane, and in its place put the match, and when we are ready, we turn up the power, and watch it light the match.
So, in summary of this lesson, so remember this is video lesson 1 to 3, week 1 of your school. What we've got is we've got a summary of the key points. I'm not going to read them. I think you can pretty much see what the key points are. But what I am going to do is, if you can pause the video here, you can copy down. These are basically the key notes that you need to have. So we've got conservation of energy law, or the law of conservation of energy. We've got the definitions of what heat and temperature are. We've got where conduction, convection and radiation occur, and then we've got the equation for gravitational potential energy. That is what students will be going through in week 1 of year 8 coming back to school. Okay, hope you enjoyed this lesson. I know it was quite a long one. Even so, I look forward to seeing you next time for week 2.